Welcome everybody. This is our series of video solutions to Quiz 6. This is from the fall 2021 semester, Math 106, which is integral calculus and differential equations. And this is our video solution to problem 1, which is all about Simpson's rule. So here we're using Simpson's rule to approximate an integral that in practice we should never be really using Simpson's rule for. So we know an antiderivative for this polynomial, and so we could easily compute that antiderivative and evaluate at the endpoint, and so by the second fundamental theorem of calculus, we can get the exact value of this integral. But you're going to humor me in this problem and compute this approximation using Simpson's rule. So let's see how we're going to do that. So first thing, I'm just going to recopy this integral, and then I'm going to use the approximately equal sign. So whenever I'm doing an approximation, I want to use a symbol that is not equal, but approximately equal. And this is the symbol we use. And I might also note here a little SR to note, right? That's just a reference to Simpson's rule. All right. So Simpson's rule tells us I need to take the length of an interval. Well, let's see what the intervals look like. So the entire domain of integration is 0 to 2, and I'm supposed to just be using n equals 2. So I just want two intervals. Well, I can cut it in half at 1, and now there's two intervals. Hey, and how long is one of these intervals? Well, the length of one of these intervals is just 1. Okay, so I'm going to take 1, and then I'm going to divide it by 3. And you say, well, why are you dividing by 3? Well, you have to go back to the derivation of Simpson's rule, and if you want, you can go check out my video on that. I'll put a link to it in the description. Okay, so now I'm going to multiply by, well, let's see, for ease, let me give a name to this integrand, call this f of x. I'm supposed to evaluate the function at the left endpoint, at the midpoint, and at the right endpoint. Except for this midpoint, I need to give it a weighting of 4. All right, the left and right endpoint will just get a weighting of 1. And because we're only doing n equals 2, I don't need to have any with a weighting of 2 in them. Now the next line actually gets an equality. I'm not approximating these values, I'm actually going to compute them, so I can use an equality. Now at 0, okay, this function is just going to evaluate to 0. That's not a problem. Then I get 4 times f of 1. At 1, I'm going to get negative 1 to the 6th, so negative 1, plus 6 times 1 to the 5th, so that'll be plus 6. All right, now I need to evaluate at 2. At 2, I'm going to get, let's see, 2 to the 6th is 64, so negative 64. 2 to the 5th is 32. 32 times 6, well, let's see, 30 times 6 is 180, and 2 times 6 is 12, so we get 192. All right, let's see. 6 minus 1 is 5, and 4 times 5 is 20. 192 minus 64. Well, let's see. Minus 62 would just give me 130. Minus 2 more gives me 128. Okay, so I add these together. I get 148, and then I have this third out front. So in total, my approximation is going to be 148 over 3, which is, well, let's see. 3 would go into 150 50 times. So this goes in 49 and 2/3 times, so 49.6 repeated. And if I actually did this computation, I would see that the correct answer, so the actual correct answer, is about 45.7. All right, it actually goes on. It's going to be a repeating deal because you're going to be dividing by a 7, so it's going to actually be 7, 1, 4, 2, 8, 5, and then that's all going to repeat. Okay, so we're off by, well, an insignificant amount actually, right? Like it's off by almost 4. Now let's see what the error bound actually would have been. Does the error bound tell us, yeah, you're going to be within 6, 8, 12, whatever? Let's take a look. So we know that the absolute value of the error is bounded by, all right, so we have this nice formula which tells us first you take the length of the interval. In that case, this is going to be a 2, and you're going to raise it to the 5th power. So I take 2, raise it to the 5th power. And then I'm going to multiply by some number, which I was always calling m, and we'll explain this m in a moment. And then we're going to divide by the number of intervals, so in this case that's also 2, raised to the 4th power, and then multiply by, there's just this constant that shows up, 180. So what is this m? M is an upper bound on the absolute value of the 4th derivative of this function f. Okay, well, I can do a little simplification before we work out this m, but that m, that's going to be the big obstruction to solving this problem. So first, 2 to the 5th over 2 to the 4th, that's just 2. And then I'm going to divide by 180. So 2 over 180 is 1 over 90. So in total, I get m over 90. All right, so we've got this thing as compact as we're going to get it without computing m, but here we go. We have to compute m. So to compute m, all right, I need to compute the 4th derivatives of f. So let's see. F of x is negative x to the 6th plus 6x to the 5th. So let's compute a first derivative. So this is going to be negative 6x to the 5th plus, now I'm going to write this in a little funny of a way. I know it's 5 times 6, which is 30, but I'm actually just going to leave 5 times 6. And then I'll have x to the 4th. And the reason is I want to factor this 6 out to make my life better. So in fact, I'll factor a negative 6 out because it just feels right. So when I factor a negative 6 out, I get x to the 5th minus 5x to the 4th. All right, switches this sign, but I really like having my leading term have a positive coefficient if I can. Okay, now I need to take a second derivative. All right, well, when I go to take the second derivative, I don't have to worry about this constant. See, that's why I factored it out. So I have negative 6 times now 5x to the 4th minus, and again, I'm not going to combine the 4 and 5, but I'm just going to make it 4 times 5 x cubed. And again, I see I can factor out a 5. So I'm going to get negative 30 x to the 4th minus what's left over, 4x cubed. Oops, 4x cubed. And you might be starting to see a pattern, but okay, we'll do another one. Third derivative, okay, I can just keep this negative 30 out front. Derivative will be 4x cubed minus 3 times 4x squared. And now I'm going to bring a 4 out, right? First time I factored out a 6, next time I factored out a 5, next time I'm factoring out here a 4. Okay, not a big surprise then. The next time we're going to factor out a 3. So the 4th derivative of x is going to be negative 120 times 3x squared minus twice 3x. I factor out the 3, and I have negative 360 times x squared minus 2x. Now, I'm looking for an upper bound on the absolute value of the 4th derivative. Now, actually, I don't really care about an upper bound anywhere, right? Really, we want it just on the intervals 0 to 2, since that's where we're integrating. It's going to turn out it's the same question in this particular case, because what does the 4th derivative look like? Well, forget about the negative 360 for a moment. X squared minus 2x is a quadratic. Quadratics are parabolic in their shape. Now, is it going to be facing up or down? Well, there's this negative 360 out front. So this tells us, right, the negative tells us it's going to be facing down. So we're going to have some downward facing parabola if we graph this. All right, can we say any more? Well, let me play this usual game and factor this as x times x minus 2. The symmetry of a parabola tells us that since this parabola will be 0 at x equals 0, and it will be 0 at x equals 2, so, all right, so if I went to graph this, I know I'm going to get a 0 at 0, and I know I'm going to get a 0 at x equals 2. By the symmetry of the parabola, the vertex must appear smack dab the middle, right down the middle, so that's at 1. So you're going to, excuse me, have a vertex there, and you're going to get your parabola looking like so. All right. Now I'm interested on the interval 0 to 2 with knowing what is this max value. Well, that's just when x is equal to 1. So let's compute fourth derivative at 1. I get negative 360 times, well, I could use either of these representations. How about this one? 1 times, well, 1 minus 2 is negative 1. Okay, multiply these together and you get 360. So that would be the height. And of course, it's positive, so I don't need to worry about the absolute value, which was in this definition of m. So the largest that m can be, or this absolute value of the fourth derivative of f can be on this interval, right, is 360. And so that's what our m is equal to. So m is 360. And so the error bound is going to be 360 over 90, which is equal to 4. So that means that the error in using Simpson's rule cannot be any greater than 4. And sure enough, what did we get? Well, our answer was, well, if you add 4 to this value, you would get, let's see, 45, let's just say 0.7 plus 4 would be 49.7. And whoo, we just squeaked in under the wire. All right. So this shows you, right, when you get that error bound, it really can get pretty close to that top end. All right. Notice they're not equal though. All right. We don't know the exact error. We just know a bound on it with 4. How could we have gotten a better approximation? Well, remember, we only used n equals 2. All right. That's a pretty quick way to do this approximation. We would have done a lot better if we'd have, say, done n equals 4 or 8 or 20, right? Any even number bigger than 2. All right, well, there we go. We can do an approximation using Simpson's rule, and we can find an error bound for that approximation.